Okay, so I hope I'm audible. So can someone please say yes or no or just thumbs up? Thanks, Saurabh. So just kindly give me one more minute. I'll set up the screen. You can just go through the contents on the screen. So for it, I'll just set up my screens. So just 1 second. Okay. Okay. So thank you for waiting, and again welcome back to the week 9 of the problem solving session for the introduction to fluid mechanics course. And in this week we will be basically starting the final chapter or final part of this course, that is the dynamic analysis of fluid flow, and we will look into the integral form of the governing equations. Okay, so right now till now we have seen the Bernoulli's equation and seen how it governs the in-viscid fluid flows, and we have seen it plays a crucial role in understanding a large scale of fluid flows around us, because we saw that there was a presence of boundary layer which was quite small and limited, which resulted in a very resulted in the confinement of the viscous forces to a very small region, and that allowed us to analytically study the fluid flows, essentially analyze the fluid flows as in-viscid flows, because most of the fluid flows that we see around us are viscid, but since the boundary the viscous effects are quite limited to a very small region in the boundary layer, so the most of the regional fluid flow can be assumed to be taken as essentially in-viscid. But again, remember that the flow is not in-viscid, given that the viscosity is not zero, but the velocity gradients are too less to manifest any kind of shear stresses in the flow field. Okay, so with that idea in mind, but still it's essential to understand the effects of viscous forces and how it modifies or the fluid flow governing equations necessary to take into account the effect of the viscous forces as well. So in today's session we will start with the Reynolds transport theorem. So one of the students have asked me about the Reynolds transport theorem in the previous classes, so I asked him to wait for today's session so that we could elaborately discuss about Reynolds transport theorem and see how we can apply it to the control system, the equations that were initially derived for the control system approach, and see how we can derive the respective equation for the control volume approach. So as we have discussed in the very first class, that why the control volume system or the control volume analysis of these fluid flow systems are necessary, it's primarily because of the fact that it exponentially decreases the cost of computation or analysis, and gives us a very proper overview of the forces or pressure distribution in the flow field. Nevertheless, the the Lagrangian analysis can give a very much more accurate results, but it's again computationally very expensive, and quite times this computational expense for the amount of accuracy that we gain by Lagrangian analysis is not that fruitful. So that's why it's quite I can say a general practice nowadays to use this Euler analysis of fluid flow analysis, and that's why it's important to understand the fluid flow problems from the perspective of the control volume approach or the Eulerian approach. Okay, so with that overview, let's start today's discussion. So this equation or any conservation equation that we initially discussed is based on this simple fundamental principle, that the net rate of change of a certain property, say if we consider a particular control volume here, then the net rate of change of that particular property within that control volume is just the sum of the net influx and we subtract the net outflux from it, and then take into consideration net generation of the property within the control volume. So This summation of in minus out plus the generation will give us the net change in of the property in the control volume, or in fluid flow terms the net rate of change of that particular property within the control volume. And that property might be anything such as force, pressure, or even the velocities. So that's why all the governing equations or the conservation equations that we essentially derive are based on this simple understanding, okay, of conservation. Then as I initially discussed, that all the as I mentioned, let me just go back here. So we discussed about the three fundamental conservation principles that we will use to understand any fluid flow analysis problems. So if I recall, those were the mass conservation, or the conservation of mass, momentum, and energy. Okay, and I also mentioned that if you're stuck in a difficult fluid flow problem, that of course has an element of control volume approach, you can apply these conservation principles and start with these conservation principles and try to attain that problem. And any examiner or professor who is going to check your answer will get a very nice idea that at least you know the basic fundamental principles that govern the fluid flow, and you will essentially get almost like you get good marks in those kind of problems. So that was a very I would say crude example of a scenario that you might experience, but is necessary. So with that idea, so all the fluid flow analysis that we'll consider from now on will be based on these three conservation principles. It is the mass, momentum, and the energy. And for the scope of this course, we will limit our analysis up to this mass and momentum conservation. Okay, and we will not go in detail in the energy analysis part. It is beyond the scope of this particular course, but it also plays a crucial crucial role in fluid mechanics if it is related to it, if it contains any heat transfer elements. Okay, but since if we do not have that for this particular course, we will only limit ourselves to mass and momentum conservation, which will see both of them in today's discussions. Okay, so as I mentioned, what is the requirement or the need of this Reynolds transform theorem? Okay, so as I mentioned, all the classical conservation equations or conservation principles were based on the control system approach. Okay, that had a fixed mass and identity. But as we know that this approach, if we follow for a fluid mechanics point of view, it's quite computationally expensive. Okay, in order to tackle that, we need to modify these equations from a control system to a control volume approach. Okay, and this transformation from a control system to a control volume approach is achieved through a mathematical transformation known as the Reynolds transfer theorem. Okay, and again I will not go in detail in the derivation of this RTT. I think that was very properly done by Prof. Chakraborty, so I will leave that as an exercise for all of you. You can, if you understand this, is more than enough. But if you want to go into the detailed derivation, which is again a good practice to know, you can go through that and understand it. Okay, just for the sake of saving time and emphasizing more on the problem solving part, I will skip the derivation, but you can look into it if necessary. So as a basic overview, the Reynolds transfer theorem is basically given by this equation. Okay, this fundamental equation, that is the rate of change of a particular property, say n, capital N, in a control system approach is equal to the local rate of change of that particular property, that is the temporal change of that particular property, dou n by dou t. It will mean that we are taking only a time derivative. So we can consider this property now in the control volume approach is a function of both space and time. That's why we only take time derivative of that particular property, where the property is considered with respect to a particular control volume. Okay, and plus the rate of outflow of that particular property minus the rate of inflow of that particular property across the control surface that engulfs the control volume. And this quantity is given by this surface integral given by rho n v dot n cap times dA, where n cap is the, or eta cap in this case, is the normal vector to the area of the control surface, and small n is the respective or the corresponding intensity property of related to this capital N. Okay, Basically, so n is the quantity that we want to conserve, or the property that we want to conserve, and small n is the n per unit mass, that is small n is equal to capital N by m. Okay, so it's a corresponding intensive property of that particular property n. Okay, so now if we consider this n in terms of a control volume integration, basically, then n, say, with respect to a particular irrespective of particular volume, would be density times volume of that particular property. So it can be replaced, capital N can be replaced by the volume integral rho n dv. So if we substitute this here in this equation, we will get dn by dt for a particular control system is equal to dou by dou t of the volume integration of rho n dv, where dv here is the elemental volume, plus the surface integral of rho n vr dot n cap dA. Okay, and here this v is the relative velocity of the fluid flow with respect to the control volume. Okay, it's very important to remember again. This v is actually we represent it as vr in the fundamental equation. So this vr is the relative velocity of the fluid with respect to the control volume. Okay, it's very important to remember. Okay, so I hope the fundamental structure of the Reynolds-Schwarzschild theorem is clear. So can I get a thumbs up or yes or no? Then I can proceed further. If it's clear. Okay. Thank you. Then let us look in the conservation of mass. Okay. So here also in this, just to again reiterate, if you look into this integration, so the integral of rho times dv will give you the total mass. Mass times this intensive property small n will give you the total property n. Okay, so that's the basic relation between capital N and small n given by this volume integral. Okay, so for conservation of mass, we just need to substitute the values of n and m. Okay, so this is basically a canonical form of the Gauni equation. So canonical form would mean that it's a generic equation. So if you just substitute a simple value in the Gauni equation, you will get the respective conservation principle for the particular property. So if you say replace this n, capital N, as say with mass, then you will get the conservation principle for mass. Okay, so if you replace capital N by m, then small n would be capital N by m, that will be m by m, that will be equal to 1. Okay, so here you just in this equation just replace capital N by m and small n by 1, so we will get the mass conservation equation in the integral form. Okay, so dm by dt for a control system would be equal to dou by dou t of volume integral of rho dv plus the surface integral of rho vr dot n cap dA. Okay, and from mass conservation, since mass can neither be created neither destroyed within a control system, then dm by dt for a control system would be equal to 0. Then this will lead us to this form the equation. Let me just write it, say in green color. So it would be dou by dou t cv rho dv plus cs rho vr dot n cap dA equal to 0. So this is the mass conservation equation. Okay, mass conservation equation in the integral form. Okay, it's the most generic form. Okay, for mass conservation. Again, there can be special cases that can be taken for this particular form, but we will see eventually how we can do that. Okay, so now let us take a very simple example that was again taken by Professor Chakraborty in the lectures. So here what's considered is it's a balloon where the air is being pumped inside the balloon. Okay, so that's why the mass flow rate of the air is given in the inward direction of the balloon. So mass of air is going inside the balloon. Okay, and since the balloon is being pumped with air, the volume of the balloon will change, and that's why the volume of the balloon is a function of time, because it will change with time. Okay, so considering uniform property within the balloon, what is the rate of change of volume of the particular balloon? Okay, in this case, so we take the control volume of the balloon as the outer surface of the volume of the balloon, and then we apply the mass conservation. Okay, so see, I am not making like I'm just going through the examples since this was taken by Prof. Chakraborty already in the class, but eventually you will get a similar question in the question and answer session for today's session. So there we will make that session interactive. Okay, so right now I'm just going through the examples because I think it was already taken so by the by professor in the lectures. But if you have any doubt in that derivation, you can stop me. So if I'm not making this part interactive, just forgive me for that. But if you have any doubt, you can just raise your hand or ask. Okay, in the derivation. Okay. Then if we apply mass conservation for this particular case, we will get that dou by dou t. Of course, the left hand side will be equal to 0. Then dou by dou t of Cv volume integral of rho dV plus this term. Okay, let me go back. Plus this term. Okay, and this term is basically the mass flow rate. Okay, so in short, you can write something as m dot in or m dot out. Okay, or basically it will be, if I write it say here, it's a most generic form. Okay, so it will basically implies m dot out minus m dot in. Okay, so I am just avoiding this integration part by replacing it by this summation of m dot out minus m dot in. Then since m dot out is 0, okay, because air is not going out of the balloon, then there is only m dot in, only the influx of the mass. This is the mass of air in this case. Then m dot out will be equal to 0, right? M dot out will be equal to 0. Then it is 0 minus m dot in. Now there is one second, just 1 second. There is one crude assumption that Professor Chakraborty had taken in the class. Okay, he considered that let us take a case where the density of the air is remaining constant or is not varying with time. Okay, it's a very crude assumption, and he in fact even mentioned that it's a very bad assumption to take, but he just wanted to give an idea like how you can analyze this kind of problems using mass conservation. Okay, so we will see why the solution is not very good. Okay, so taking a very crude assumption that the density of the air is not a function of time, then we can take this density out of the time derivative. Okay, then with that approximation, then rho can be taken out of the time derivative, then it will basically be rho times dou by dou t of of dv. So it will basically give you v, integration will give you v, the volume of the control volume, then it is d by dt of vcv. Okay, so now if we just rearrange the equation, we will get that, of course this will go to the left hand side, it will become plus, right? So we will get rho times dvcv dt is equal to m dot in. And why we have taken complete derivative? Because since volume is only a function of time, if I go back here as given in this particular problem, then it's the partial derivative can be converted to a total derivative. Okay, then dvcv dt is equal to m dot in by rho. We take rho in the denominator. So this is a very crude approximation for the rate of change of the control volume for a inflation of balloon, in the case of inflation of balloon. But Professor Chakraborty would have mentioned very explicitly that this is a very crude answer. Why? Primarily because this is not the case. Since the volume of the balloon is not expanding at the rate at which we are blowing air inside it, that's why the density, the value of density would not remain constant. Okay, it will vary with time. Moreover, since the value of density is air is highly compressible in that particular scenario, so blowing of air within a particular confinement will result in the density to vary with time. Okay, that's why this is not a very good approximation. Okay, that's why this answer is a very, very rough way, I would say very crude way to assume this particular problem. And Professor Chakraborty might have mentioned that this kind of problems of inflation of balloon and where the boundary of the control volume is changing with time is one of the very hardest problems in fluid mechanics. Okay, so with that overview, let us now take some assumptions. Okay, how we can simplify our analysis. So let me again write the generic form of mass conservation just for your reference. That is sorry. this was generic form, right? Plus control surface rho VR equal to 0. Okay. Now this is the generic form of the mass conservation. Okay, so now let us make some simplifications or some modifications to the equation. So what it is said that now let us consider a non-deformable control volume. So if the control volume is non-deformable, okay, then what we can say is the volume of the control is not a function of time. Okay, so it will remain constant with time. Okay, so if it is deformable, then the volume of the control volume will change with time, which was the case of, let me go back here, which was the case in the case of inflation of balloon. But since this is non-deformable control volume, then the volume of the control volume will remain constant with time. Okay, for example, say a flow through a pipe, the volume of the pipe remains constant. Okay, it's a rigid boundary, so it remains constant. So if we take the outer surface of the pipe as our control volume, then it's an example of a non-deformable control volume. So in that case, volume of the control is not a function of time. That's why we can take this time derivative inside the integral, representing that only the density is now a function of time. Okay. Now let us take a second assumption, that is a stationary control volume. So now, and we will see that most of the, I will not say most of the, but most of the essential engineering control volumes that we will deal with in your study or work will primarily deal with stationary control volume. For example, say flow through a pipe, so flow through an bent elbow, or flow, or say you're modeling a boiler. In those cases, the control volume that you are simulating or analyzing is a stationary control volume. Okay, so in that case, the relative velocity of the fluid with respect to the control volume will be equal to the absolute velocity of the fluid in the across the control volume. Okay, so then we can write VR is equal to V. Okay, there is the absolute velocity of the fluid flow. Okay, so in that case we can now replace so now in that case we can replace VR by V. Okay, we can replace VR by V. So if we do that, now we can simply modify the equation even further. So we can write the equation as this one. Okay, so you can see here we have replaced VR by V. So now using Gauss divergence theorem. Okay, so this was the question that was asked by one of the students, the application of Gauss divergence theorem. So here we essentially apply the Gauss divergence theorem. Why? Because we are dealing with a scenario where a particular vector property, that is the velocity in this particular case, is analyzed in a enclosed surface, and this surface is essentially enclosing the control volume that we are analyzing. Okay, so if these scenarios are satisfied, then we can apply Gauss divergence theorem to replace the surface integral with a volume integral, which is essentially done by using this particular identity. Okay, where f is the vector function and n cap is the normal vector to the particular normal vector to the area which encloses this vector property, and nebula is the, so, and this delta is the nebula operator. Okay, that is I cap plus d by j cap plus d by dz dou by dou z k cap. Okay, in the Cartesian coordinates, of course. So then using that identity, we can now replace this surface integral by a volume integral. So if we do that, we can write this equation now as this one, where we have now taken a common volume integration across both the terms, because now the integration is same over the same control volume, right? That's why we can now sum these individual terms together and then take the integral. Okay, so now if we consider this integration to be 0, then it can only be 0 when the integrand itself is 0 for a arbitrary choice of control volume, okay, or the elemental volume dV. So if that's the case, then dou rho by dou t plus nebula dot rho v should be equal to 0, which is exactly the mass conservation equation that we have obtained in our previous classes. Okay, while we are dealing with when we were obtaining this equation from, say, a control volume analysis, that we drew a particular cuboidal shape and did the mass conservation or the momentum mass conservation through that particular fluid flow from the particular control volume, then we obtain the same equation. Okay, so we are getting the same exact equation using RTT now. Okay, so that shows the accuracy or the effectiveness of using RTT in this kind of problems. Okay, and similarly, if we can obtain the mass conservation, sorry, the momentum conservation as well, by just replacing, if we go back here, n by the momentum mv, then small n will be the velocity vector v. Then if we replace these values in the canonical form of the RTT, then we will get the momentum conservation equation. Okay, and in that case, dn by dt will not be equal to 0, because rate of change of force will imply to another very interesting property, that is the force, the net force that acts on the control volume. Okay, so I hope it's clear till now. Okay, so now let's again take an example. Okay, again this example was taken by Professor Chakraborty, but I'm just reiterating it again, so that first of all our concepts are more consolidated. Secondly, if there's any remaining doubt in that particular problem, then we can clarify it. Okay, so let us take a very say a case where there is a jar here, there is a container, okay, of this particular shape, which has two elbows or two arms. You can say two arms. Okay, this is the shape of the flask that we have taken into consideration, and it has two arms. Okay, and fluid flows inside the left arm here and goes out this arm. Okay, goes out from this arm. Okay, the question is, in this case, all the I say terms are already mentioned. So the thickness of this particular arm is say h by 2, and the thickness of this arm is say capital H. Okay, twice this with this thickness. Area at the left arm, which is the inlet, is a naught, and the velocity profile at the inlet is given by u infinity, which is a constant velocity profile. Okay, and in the case of the right arm, where the flow is going out, or the outlet, the velocity profile is given by this particular equation, which is basically a second order polynomial or a quadratic polynomial, because it has a second order dependence on the spatial coordinate, it is y. Okay, so velocity profile is given by this equation, this relation, and the question is, for a constant density fluid flow, determine the value of u naught. Okay, so in this case you will see that now you are having to in this scenario you have to find the velocity or the you have to find the velocity term. Okay, the u naught. Okay, so in this kind of cases you can now simply apply the mass conservation. Okay, in this equation you will see that you will get a proper relation to apply proper relation to find the value of u naught in terms of the properties that you already know. Okay, so what are terms that you already know? That is, you know, h is already given in the problem, which is defined, and you know u infinity, also a naught. Okay, so these are terms that you already know, and with the help of these known terms you need to find relationship, so that you can get a value of you can get a functional form of u naught. Okay, and other assumption that we can consider is rho is equal to constant. Okay, that's another help that we get from the question. So now if we apply mass conservation, so again let me write a generic form, or let me do one thing that would be much better. What I can do is I can take this equation, copy it, and use it all the time that I want. Then it would be better, right, rather than writing it again and again. So this is the generic form of your mass conservation that was considered here. Okay, you can start with this. It's always a good practice to start with the generic form, so that you can get a good idea which terms you are eliminating, whether the elimination of those terms are correct or not. You can understand when you start with the generic form of the mass conservation, or any conservation equation that you are starting with. So now since density is constant, so it will remain a constant. In fact it can go out, and okay, it can go out. So again, sorry, it will get, this equation will be simplified as say rho times this. Okay, sorry, uh, it will simplify as rho dou by dou t of dv, or it will basically be rho dou by dou t of vcv. Okay, so now since v is not a function of time, okay, since this is a rigid container and the control volume that we have chosen is such that it's not changing with time, that's why the control volume is not a function of time. That's why this will be equal to 0. So this essentially means that the first term in our conservation equation in mass conservation is equal to 0. Okay, so the only term that can give us some idea or hint towards solving this problem is that the second term, okay, the surface integral term that includes that encompasses the mass influx and mass outflux term. Okay, so and again here, since the control volume is stationary, okay, that's why VR will be equal to V, that is the absolute velocity of fluid flow. Okay, that's what we have actually written here. So this is the equation that we have to deal with. Let's see whether it gives us some idea or not, how to find U naught. So, and this one again, as I mentioned previously, this is basically the net outflux from the container or the control volume. So it will be m out minus m dot in. Okay, net mass flow rate out of the control volume. So at the area A naught, that is at the left arm, the fluid is going inside the control volume, so it is the inlet. Okay, so net mass influx. So since the velocity profile is already defined, that is u infinity, so it will just, m dot is basically given by rho a v, right? So it will be rho constant density, a is your h by 2, and b, okay, b is given the width of the, let me write it, b is equal to width, okay, width of this arm, width of the arms, okay, into the paper. Okay, so now area would be h half h by 2 into b, right? This will give you the area times the velocity. Velocity is u infinity. Why we can write u infinity so easily? Because it is a constant velocity profile. Okay, it's constant, so the integration that you will just give you the same result. Okay, that's why it is u infinity. Okay, and it will have a minus sign. Why? Because the direction of the normal vector and the direction of the velocity are opposite to each other. That's why their dot product will give you a negative sign. Okay, that's why it is minus, so it is written here. The complicated part is the outflow, or the right arm where the fluid is going outside the control volume, because the velocity is not constant. It's in fact a function of y, and it has a quadratic dependence. Okay, so it's not constant, basically it's not constant. So in order to do that, this m dot out, this is equal to m dot out would be equal to, u is given by this one, right? V, sorry, v dot, so v is given by, let me go back, u naught into 1 minus y1 square by h square, okay, times the area, that is b, that is constant, with times dy1, okay, the elemental, say, elemental width of the area that you are taking. Okay, so if we carry forward this integration, right, so we'll get that this would be equal so if I write it if we just write it again to make it more clear, so it will basically be, if I write this one here, it would be integration of minus h by 2 to h by 2 u naught 1 minus y1 square by h square b dy1 minus u infinity h by 2. Just 1 second, okay, it's so sorry for the disturbance. Sorry for the disturbance. Okay. Yeah. So it is minus u infinity h by 2 into b. Again, you may say minus and y is not cancelling out. Okay. So see, this one. Let me write it in other color. This one basically mean that the total sum. Okay. So it will basically, if you just don't consider the sign from beforehand, okay, then it will basically mean net summation of the mass flow rates. Okay, it will be say m dot out plus m dot in. Okay, is the is how it, what this actually means. But since we know that at the inlet the direction of the uh, velocity vector and the area vector are opposite to each other, so this will automatically include a negative sign here. Okay, that will result in the overall formula to give us this one, sorry, something like this. Okay, and you may ask, what then, why we are just not doing something like this and considering a generic formula. Okay, this will eventually see in the next problem, so I'll let you know there. But say you are dealing with multiple inlets and multiple outlets. Okay, and say you are dealing with say 10 inlets, 10 outlets, and of course the direction of velocity are also given, but it's again a very tedious task to individually point out again and again. So it's just a better way to write all these terms, all the mass flow rates, and then accordingly put the sign of the put the respective sign by considering whether the flow is going inside or outside the control volume. Okay, that will give you the proper signs. Okay, so it's a it's a general practice, but I hope it is clear. I just wanted to let you know why we are not doing something like minus minus, why it is not becoming plus. Okay, so it's just a dot product of the velocity and the normal vector gives us this minus sign. Okay, at the inlet. Okay. So yeah, so this will be equal to 0, right? So again, this if it goes in the right hand side, so it will basically be this. Okay, now if you carry forward the integration a bit further, so you will get that u naught times 11 by 12 h is equal to u infinity h by 2, or u naught is 6 by 11 into u infinity. Okay, so this is what you will get. So here we got relationship between u infinity in terms of u naught in terms of u infinity. Okay, so this is your solution. So is it clear till now? Okay, yeah. So I was mentioning about the type of problems. Okay, so you will see that most of the say problems where you need to apply mass conservation, or let me say in another way. Okay, so if the problem that you have in hand is involving a scenario where you are having to find the expression for velocity, or say the expression for mass flow rate. Okay, so in those kind of problems you should essentially apply the mass conservation equation. Okay, again it seems so generic, but it seems so like obvious. If they're asking mass flow rate, then say they directly apply mass conservation equation. But I'm just saying, like, if there's a question that asks you to find an expression for mass flow rate or say velocity, which was the case in this problem, then it will suffice that if you only apply the mass conservation equation, you will get a relation. Okay, for this kind of problems, this control volume type of problems. But say if you are having questions that has that deal with forces, for example drag forces that act on the controls volume or control surface, in those kind of scenarios you need to apply both the mass conservation and the momentum conservation. So it will happen that this will come up in levels, like when you approach the problem from mass conservation, those kind of problem with mass conservation, you will get some hints that you can use to solve the momentum conservation equation. That will eventually see in one of the following examples that I will take today. But this is the way, like, how these are applied. Okay, so this thing might seem quite obvious, but still I just wanted to point out. Okay, so let us take another example. Before that, okay, it's fine. Yeah, So in this equation, in this question, here you'll see there is no outlet as such. Why? Because in both of the arms, again the control volume is the same, but the scenario is different now. Okay. So what's happening is that now in both of these arms, the fluid is going inside the control volume as shown by these arrows. Okay, as shown by these arrows. And what's happening is that since the fluid is going inside the control volume, there's let me just go to this equation. Okay, so it is in minus out plus gen is equal to net change. Okay, so what was in the previous case, what was there? In the previous scenario, we had both of these terms. This was equal to 0, and if in is equal to out, then it will imply that the net change of the property is equal to 0, which was mass in that particular case. So mass net change of mass inside the control volume was 0, because mass in was equal to mass out. But in this particular case, since mass out is equal to 0, since this is equal to 0 and this is also equal to 0, then it will imply that since there's a positive influx of mass flow rate inside the control volume, it will imply that there must be a change of the property inside the control volume. Okay, this will correspond to a particular change that we need to take into consideration. So again, in this case, since we are dealing with mass, so the mass inside the control volume will change, or intuitively we think it will increase. Okay. So in this case, what's happening is that since both of these arms are putting fluid inside the control volume, the mass of the fluid inside the control volume is increasing, which is resulting in the increase in the height of the fluid level inside the control volume. Okay. So our task is to find an expression for the rate of change of this height. Okay. Okay. And again, rate of change of height. Height is say I should write more correctly as h dot. Okay, so again h dot, we are dealing with h dot. H dot will basically mean that it's a rate of change of a particular displacement, okay, or distance. Then it's one way or another corresponds to velocity. And since we are dealing with velocity, again the use of mass conservation will suffice to solve this problem. Okay, so that's how you can think about it. Okay. And again, there was a very nice discussion taken by Professor Chakraborty, like why to choose a control volume of this form that is given by these red lines, okay, like which engulfs the inlet and the outer surface or the upper surface of the fluid level, okay, in the control volume. Why not consider a control volume of this form? Okay, seems more simpler and more generic. And there was a very nice conclusion taken out from this discussion by Professor Chakraborty, that we have to use a control volume as such that we get most of the knowledge about the velocity profile in the control volume, because the knowledge of the velocity profiles is already known to us in these particular scenarios, okay, in these particular inlets. Thus it's better to choose this kind of control that contains most of the knowledge regarding that contains knowledge of most of the velocities in the control volume. Okay, for example, okay, this is the particular case, because we know that velocity is constant in the inlets, okay, that is equal to v1 and v2, but we do not know how the velocity varies at these elbows. We do not know how it varies. It may not be even constant. Of course it will be constant if you're considering viscous effects. It will form some special velocity profiles, something like this, it will change in a parabolic form. Okay, and since we do not know that, it's just better to choose the control volume as such that we know the velocity profile at the inlets or the outlets. Okay, and similar case, if I go back, it's also done here as well. Here, even if we do not know, here of course we have chosen the velocity profile such that we know the velocity at the inlets and outlets. So here we know the velocity at the inlet, and here also we know the velocity profile at the outlet. Okay, so that's why the choice of control volume is also very essential or crucial in solving these kind of problems. Okay. Yeah. So now again let us apply the mass conservation. Again the first term would be 0. Okay. First term will now not be equal to 0. Why? Because the control volume will keep on changing. Why? Because since the height of the liquid is changing with time, that's why the first term now will not be equal to 0. But since density is equal to constant, we can take out density of the volume of this volume integral and even the time derivative. So we can write it something like rho is equal to d into d, rho is equal to dAh by dt, where Ah represents the instantaneous volume of the fluid inside the container. Okay. And since height is also only a function of time in this particular case, so we can replace the partial derivative by complete derivative here. Okay. And the other term, the second term will remain as such. And now since the velocity at the inlet is constant, we do not need to worry with the integration. We can directly write it something like m dot is equal to rho av. So we can write something directly as that. So at the left arm it would be again minus sign, because the direction of the area vector and the normal vector from the, or the direction of the area vector and the velocity vector are opposite to each other. So it will be minus rho v1 a1. Again at the right arm again it will be the same, because it's velocity profile. So the velocity is opposite to the direction of the normal vector of the area, so it will be minus rho a2 v2. Okay. So if we combine both of these terms, and again this will be equal to 0, we combine that, we will get that rho a dh by dt minus rho v1 a1 minus rho v2 a2 is equal to 0, or dh by dt is equal to rho v1 a1 plus rho v2 a2 by rho a. And since density is constant, we can write dh by dt is equal to v1 a1 is equal to, so dh by dt is equal to v1 a1 plus v2 a2 by a. Okay. So I hope this was clear. Now let us look into the momentum conservation. So as I was mentioning previously, it's again a canonical form of the governing equation, is RTT. So just change the value of n, you will get the respective conservation principle. So for momentum conservation, replace n by the linear momentum, that is mv. So d by dt of mv for the control system would be equal to the net rate of change of force inside the control system, and limit delta t equal to 0. Again this was discussed in the lecture, so I will suggest that you go back how this is achieved. Again this was discussed in the previous sections as well, like why the analogy between, in what context or in what scenario the analogy between the control volume and control system and the control volume approach is valid. Then we saw that the rate of change of properties should be very infinitesimally small, so delta t should be very small. That's why then in that case the net rate of change of the control system would be equal to the net rate of change of the control volume. Okay, so here in this case dmv by d by dt of mv for the control system will be equal to net rate of change of force in the control system, and this would corresponding to the net rate of change of force in the control volume. Okay, so if we do that, then replace small n by capital V, and again here small n by capital V, but VR will remain as such. So we'll have that d by dt of mv for the control system is equal to dou by dou t of volume integral rho v dv, where v is the absolute velocity of the fluid flow, plus the surface integral of rho v vr dot n cap dA, where v is the absolute velocity here, vr is the relative velocity of fluid respect to the control volume, and this will correspond to net force or the net rate of change of momentum or linear momentum, that will correspond to net force that acts on the control volume. Okay. Now let us take one example. I don't think this was taken in the lectures, because I think this will be taken in the next this week 10 session as a continuation of the conservation of linear momentum. But this example I took because I think that some of the questions that we will need today have the similar case. Okay. So let us start. So the question is, this is a boundary layer problem. Okay. So there is a flat plate and fluid flows above this flat plate, which generates this boundary layer, and the velocity profile at the rightmost edge of the plate is given by this particular shape, and we know the form of this particular shape is given by u by u infinity, or basically the velocity profile. This u by u infinity is equal to y by delta minus 1 by 2 y by delta whole square, where delta is the boundary layer thickness. Okay, and the incoming velocity is given by u infinity, which is the free stream velocity that is constant. Okay, that's why the velocity profile is constant in this particular case. Okay, just one second. Yeah. So now let us consider a contour volume of this form given by these green dotted lines. Okay, so we are choosing it as such that we know the velocity at least one of the outlets, that is here in this case we know the velocity profile at BC. Okay, just one second. Yeah. Okay, so the question is for rho equal to constant, given that the control volume is non-deformable, so it is basically this boundary layer remains as such, and B is the width of the plate inside the paper. Okay, what is the net drag force that is exerted by the plate on the fluid? Okay, so this is the hint that I was trying to discuss, that here they are asking about net drag force. So if they are asking about net drag force, if force is coming into the picture, then definitely you need to apply the momentum conservation. But the catch is that starting with the momentum conservation directly will not give you the solution as such, because the problems that they are designed, they are mostly designed as such that you need to start by the application of mass conservation. Then application of that mass conservation will give you some of the hints or some of the preliminary solution that you require to start or to solve the momentum conservation equation. Okay, so that's how the questions are basically designed in basic fluid mechanics course. So that's why I was trying to hint towards that. Okay, so with that idea, let us now start with mass conservation. So since the density is constant and the control volume is non-deformable, so if both of these scenarios are satisfied, okay, again remember carefully, if both of these scenarios are satisfied, that is density constant and non-deformable control volume, then the first term in the mass conservation can be essentially neglected. Okay, so I am just neglecting it directly here, so it is equal to 0, and now let us deal with the surface integral part. Okay, the mass influx and mass outflux part. Okay, so in this case, here the mass outflux, that is, it will be from, since since the fluid flow is coming through this direction, so the mass can either, of course this is going outside from this particular surface, from this particular edge, so it is net mass outflux, but here we do not know, so here it can essentially be a net influx. Okay, so it will essentially be net influx, because since it's a closed edge here, so mass has to go through this particular edge for the mass conservation to be satisfied. Okay, so we write rho integrated from 0 to delta naught, where delta naught represents boundary thickness at this particular edge. Okay, and again delta or boundary thickness is a function of x, that is the distance from the leading edge. Leading edge basically the point from where the boundary layer starts or the plate starts. So if this is x, then boundary layer is a function of x. Okay, so as the distance from the leading edge increases, the length of the boundary layer will also increase up till the point where, okay, it will go on increasing, but say if you are dealing with flow through pipes, then it will increase up to the entry length, or the up to the point where the boundary layer merge together. Okay, so yeah, but here since we know that the boundary layer the plate ends at this particular point, then the boundary layer at this particular point is given by delta naught. Okay, it's already given in the question. So the mass flow rate is given by rho times u dy into u dA. Basically it is dA, so elemental thickness would be b, that is the width, times this particular length, it is dy. Okay, so elemental area would be b into dy, or dy into b, it is written here. Okay, and it should be integrated from 0 to delta naught. plus m dot ac. We are just summing it up. We do not know the sign of the m dot ac right now. It should essentially be negative so that mass conservation is preserved. Okay. Then m dot ac would be essentially, then since this is equal to 0, then m dot ac is given by minus rho times 0 integration of 0 to delta naught u dy into dv. Okay, so let us consider this equation number star or a. Okay. Then from momentum conservation, again the first term would be 0. If I just go back here, since density is constant and the control volume is stationary, then again this term will also be equal to 0 in the case of momentum conservation. So first term is 0 here in this case. Okay. Then again we deal with the net momentum influx and not net momentum outflux terms. Okay. So here, since if I go back here again, let me just go back. See, mass conservation is a scalar equation. Why? Because mass is a scalar property. But momentum conservation is a vector equation. Why? Because momentum itself is a vector quantity. So instead of, if you are not solving the vector equation as such, then it will have its defined components. Okay. And drag force by its very nature is a force that acts along the direction of fluid flow. Okay. So there is a concept of drag force and lift force. So so drag force will act along the direction of the fluid flow, and the lift force will act in the direction perpendicular to the direction of the fluid flow. Okay. So since we are asked to find the net drag force, so we need to find the net force along the x direction. So that's why we deal with the x component of the momentum equation. Okay. So if you just substitute the values of u here, u, that is the velocity component along the x direction in this particular equation, you will get that 0 to u, 0 to the integration of 0 to delta naught rho u b dy. U will remain the same because the control volume is stationary. So v and vr will be same. So it will be u times u and b dy. And here at the, let me go back here again, at the inlet, which is basically this edge AC, then the velocity at this particular case along the x direction is the u infinity, so it will be u infinity times m dot AC. Okay. And m dot AC is again given by this particular relation which we got from the mass conservation. See the how we are getting correlating it, all of them. Okay. So u infinity times m dot AC. So to solve it or to proceed further with fx, you need to know u infinity. So you need to know m dot AC, which is given by equation number A. Okay. So if you substitute it, the value of m dot AC here, you will get f of x is equal to rho b times integration from 0 to delta naught u square dy minus u infinity integration of 0 to delta naught u y dy. Okay. So let us consider this as equation number 1. So this is the formula for the net drag force that acts along the x direction. Again, just substitute the value of u in this equation, you will get the result in terms of u infinity and delta naught. Okay, on rho b. But now let us consider a second scenario. Okay, let us consider a different type of control volume. Okay, so initially we saw that our initial control volume was of this form. Okay, that was just following the shape of the boundary layer. Okay, but now let us say that I am not liking this particular shape of the inlet. Okay, this seems quite cumbersome. Like most important because here the velocity that's incoming is not normal to the inlet. It's coming in a particular angle. Okay, and I'm feeling a bit uncomfortable while solving this kind of problem. Okay, so because now if I have to find the components, then I have to find the angle between the velocity and the normal vector to this particular control surface, which is again a curved shape, and it's quite cumbersome, it's quite difficult. Okay, so now let us take a scenario where I choose a control volume of this form, okay, of this form, okay. So this example is not yet taken by Prof. Chakraborty, so you may not know this, but let us just try to look into it. Okay, Prof. Chakraborty will take this in the next lecture, but this example is necessary to solve problems in today's question Q&A part. Okay, so let us take control volume of this form. Okay, as shown by this green line. Now you may ask, now I have made it even more complicated, because initially we only had to deal with 3 edges, that is 1, 2 and 3, where one of the edges had no mass flow rate because it's not a porous surface, so there is no fluid flow in the from this edge. So fluid is only coming in through this particular edge in the previous control volume and going out from this particular. So it was quite simple, but now I made it more complicated by adding one more surface. It is now total 4 surfaces. There is 1, 2, 3, 4. Okay, but now what I say is that now I'm assuming that this surface or this edge of the control volume is a streamline. And if you recall, there is a very interesting property of a streamline. Could anyone state that what property of streamline that we can use to simplify this problem? You can give it a try. Okay, so the thing is that there's a very interesting property of streamline, that it is that there is no flow across a streamline. If you recall, there's a very interesting property of streamline that there is no flow across a streamline. So if there is no flow across a streamline, then we can just neglect the mass flow rate across this particular edge. So we are again now limited to one inlet and one outlet. So there is no flow across this edge, so because it's a streamline, that's why you are only dealing with these two, this inlet and outlet. Okay, so now in this case, now inlet is quite satisfactory. Why? Because it is normal or perpendicular to the incoming flow, which in many ways simplifies the analysis. Okay, so that's why I would like to choose this kind of control volume at least in this kind of boundary layer problems, where one of the control surface is a streamline, one of the edge of the control volume is a streamline, that helps us to simplify the analysis. Okay, so did you understand this part? Like, is it clear till now why we choose this kind of control volume? Or if there's any doubt, you can ask. Okay, or else I will proceed further. So you eventually understand more when you start solving some problems. So let me quickly finish this part and then start the Q&A portion. Okay, so again, from mass conservation, the first term, the time derivative part is 0 because density is constant, volume is constant. Volume is not constant but independent, essentially constant is independent of time, it's not deformable. So the first term is 0. Again, at this edge BC, then it is the mass flow is given by rho times integration of 0 to delta naught u divided b. That is exactly same as the first term, exactly same as this one. But in the case of the inlet, here the velocity is again constant. It is minus u infinity, again taking into consideration normal vector of the velocity and the area vector. They are opposite to each other, so it will encompass a minus sign, times rho, that is constant, and integration from 0 to h naught into b dy, so it will basically be into b h naught. Okay, it will basically give you b h naught. So let me just write it. So it will be 0 equal to rho times 0 to delta naught u dy b minus u infinity rho b h naught. Okay, So if you simplify it, you will get H naught as rho u dy b divided by u infinity rho and b. So this will cancel out. So you will get H naught is equal to 0 to delta naught u dy by u infinity. This is exactly that I have written here. Okay. So now let us look into the linear momentum conservation. Okay. So again the first term will be 0. Why? Because if I go back to this equation, since again density is constant, so this will come out of the integration, and since both velocity and volume are independent of time, okay, that's why this time derivative of this volume and the control velocity and the control volume will be equal to 0. So that's why the first term will be equal to 0 in the case of a velocity being independent of time, non-deformable control volume, and a constant density problem. Okay. So first term is again 0. Then again we just need to deal with the momentum influx, that is the momentum influx terms at the inlet and the outlet. So at the outlet we'll have rho integrating rho times 0 to integration of 0 to delta naught u squared dy b, again exactly the same as this term, but the next term will change. It will be rho times integration of 0 to h naught, that is, if I zoom out a bit, it will make it a bit more clear. So integration from 0 to h naught. Okay. Then incoming velocity is u infinity. Again take into consideration the sign of the normal vector and incoming velocity. It will again be the absolute velocity of fluid flow. Why? Because it's a stationary control volume. So it is minus u infinity dy times b. So if you integrate it and simplify it, you will get that fx is equal to rho times integration of 0 to delta naught u square dy b minus rho b u infinity square into h naught. Now h naught is given by this equation, okay, in which you would have not got if you didn't apply the mass conservation. Okay. Now if you see the value of h naught here, you will get that fx is equal to rho b integration of 0 to delta naught u square b dy. So u square dy minus u infinity integration of 0 to delta naught u dy, which is exact, if you look, is exactly same as the equation that we got here. Okay. So now I think it's time to start the Q&A part. So let us start with this question. Okay. So this question number 1. So there are a lot of questions and limited time because the session was started say 18 minutes late. I'm sorry for that. It was unavoidable. But let us try to solve as many questions as we can. Okay. So the thing is, there is a flow between two plates. Okay, as shown here. Okay, and the incoming velocity profile is given by u naught. Well, let me just read the question. Incommensurable steady flow in the inlet between parallel plates are shown in the figure as is uniform with u is equal to u naught is equal to 8 cm per second. So u naught is 8 cm per second, while the downstream flow develops into a parabolic laminar profile. Okay, so downstream flow at the outlet is a parabolic laminar profile. Okay, where u is az times z naught minus z, where a is a constant. If z naught is equal to 4 centimeter, the fluid is an oil with rho is equal to n91 kg per meter cube, and nu is, which is the kinematic viscosity, is 114 times 10 to the power minus 6 meter square per second. What is the value of u max? Okay, u max. So again I will give you carrying forward the hint that I already gave you. Since you are having to deal with scenarios where you need to find velocities, so you need to find u max in this particular case, use of mass conservation will suffice. Okay, so the direct hint is that you have to choose a control volume, of course, which should be stationary and density is constant. So you will be dealing with mass conservation with the first term being 0 and the velocity, the mass influx and mass outflux terms will remain. So find the corresponding values of m dot at the inlet and m dot at the outlet, balance them, and you will get some hints. Okay, so try it out. I will give you say 5 minutes. So we are very I would say have to very strict with the time limit because we have to solve a lot of problems. So let us wait for, I'll give you 5 minutes to try this problem. I hope the problem is clear, and try to find out the value of umax. So the first task would be to find the value of a. A is also not known, so I need to find it and then try to find the value of umax. Okay, so I hope the question is clear. Let us wait for 5 minutes and then see. Okay, try it out. So I think one more minute. Any progress? Any progress in the solution? I will wait one more minute and then I will discuss the solution again. It's fine. So it's the very first week or very first time we are discussing this kind of solution approach. It's something quite new. And again, from personal experience, I can say it takes a bit time to adjust or apply it properly, but uh, with practice, it will eventually come. Okay, it's fine. So okay, I think time's up. No issues. Let us look into the solution and then let's try to understand. Okay. So I think the problem is clear. Now let us see how we can solve it. So this is again the problem that we have in our hand. So I think all of the thing I already discussed. First term would be 0 because density is constant and control volume is if you just do control volume something like this. Okay, control volume is, or I'm sorry, it should ideally be something like this. Okay, then control volume is stationary and it's non-deformable. Okay, so this term will be equal to 0, this already equal to 0 as shown here, then we are only dealing with this term. Okay, then if we solve for this term, you will get that at the this we will get z naught times u naught. This is the, since density is constant, so rather than dealing with mass flow rate, you can deal with the volume flow rate. Okay, because if you even if you keep density here, so it will get cancelled out, so we're just cancelling it out from both the sides. So you'll have z naught times u naught is equal to integration from 0 to z naught u into dz. Okay, why are you integrating here? Because the velocity profile here is not constant. It's not constant. Okay, it's varying with space, so you need to carry forward the integration to find the net volume flow rate or mass flow rate, whichever maybe you're dealing with. Okay, so you'll have u as az times z naught minus z into dz. Okay, integration of 0 to z. Then if we integrate it, we will get that it will be equal to a times z square by 2 times z naught minus z cube by 3 from 0 to z naught. If you substitute the value of z naught, you will get z naught times u naught is equal to a times z naught cube by 6. Okay, if you now solve for this, because you know the value of u naught, z naught, you need to find the value of a. Okay, that's important to find the value of u max. You will see why. Then a is equal to 6 u naught by z square is equal to 6 into 8 times 16, that is equal to 3. Now there's one more thing that we need to know, that was the catch for this problem. That is the understanding of the maximum velocity. So if you look into this velocity profile, okay, so that is u is equal to a z naught minus z. Okay, this is the velocity profile. So you'll see that even if you look at just from this particular case, the maximum velocity is obtained when z is equal to z naught by 2. Okay, or at the midpoint of the this particular velocity profile. Okay, and you will eventually see that for flow between two parallel plates, when we will discuss some exact cases of Navier-Stokes equations, you will see that the maximum velocity occurs for flow between two parallel plates at the midplane. Okay, so u max is at z equal to z naught by 2. Okay, so that was the catch of this problem. Just substitute the value of z as z naught by 2 here. You will get u max, you will get u equal to u max. Then u max is equal to a times z naught by 2 into z naught minus z naught by 2. Now if you substitute the value of a and z naught, you will get that u max is equal to 12 centimeter per second, which is option number B. Okay, now let's look in the next question. Sorry for rushing. There are lots of questions that we need to solve, but limited time. Okay, so this is the problem I dealt, because this is we dealt with this kind of problem because I knew that there was one more question here in today's session, so I just wanted to give you a slight hint. Okay, so the question is again quite similar, but let us go through it once. A fluid of constant density rho flows steadily past a porous plate with a uniform free stream velocity u infinity, as shown in the figure. Okay, constant suction is applied along the porous section. Okay, the porous section is given here. It is constant suction, so the velocity profile at this particular edge of the control surface is given by v is equal to minus u 0.1 u infinity, where u infinity is here. Okay, and it is in the negative z direction, negative y direction, which is given by j cap. The velocity distribution at the section CD is given by u by u infinity, that is velocity profile at this edge is given by this velocity profile. Okay, quite similar to the one that you already dealt with. Determine the mass flow rate across the section BC, assume unit with unit paper. Okay, so again one more hint, since you have to only deal with mass flow rate, then dealing with only the mass conservation equation should suffice. Okay, so with that idea, can you try it, or so I will think that just for saving time, I can discuss this problem and then maybe you can try the next problem. Okay, that will be much more much better. And why I'm doing so, because this problem again includes this, it will include extensive integration. So I also won't do it, I will just show you the solution methodology, then you can just try to see whether it matches with your results or not. Okay, so okay, so this is the solution that we have. Again, this notes I will share to you, so you can just compare it with it once, and then you can try to solve similar problems in the assignments. Okay, so velocity distribution at CD is given by u by infinity is equal to 3 by 2 y by delta minus half y by delta cube. Okay, so this dependence, silly mistakes, what we can do is, since we have dealt a question with y by del square, you may replace it directly with square rather than looking at the velocity profile properly. So when you look at it is y by delta cube. Okay, so applying mass conservation over the CV control volume given by A, B, C, D. Okay, and considering the non-deformable control volume, you will get that you will get that the integration of the surface integral of rho VR dot n cap d is equal to 0, or m dot AB is equal to m dot AD plus m dot CD plus m dot BC. Okay, so there's only one inlet and all other edges of the control surface are essentially outlets. So mass is coming in from AB and going out of all the other edges of the control volume. Okay, so we need to find BC. So m dot BC is equal to m dot AB minus m dot AD plus m dot CD. Then m dot AB, I think I need to zoom out a bit. Yeah, so a bit more. Yeah, so m dot AB would be simply u naught times delta, that is boundary thickness here, times u infinity. Okay, since the width of the control volume is unity into the width of the into this paper, then perpendicular to these papers, right? So of course there is a 1 here, but you can just ignore it for this calculation. Okay, so it will be rho times u infinity into delta minus m dot AD would be again 0.1 u infinity rho times L because the area would be, in this case, would be L times 1, so area is rho AB, right? So rho times L dot 0.1 u infinity. Okay, is shown here, plus the mass flow rate from the surface CD, that will be rho times integration from 0 to delta u dy. Okay, so the only tricky part in this problem is carrying forward this integration, with I myself have not done. Sorry for that. So but I know the solution, that eventually if you solve it, you will get that m dot BC is equal to rho times u infinity times 3 by 8 delta minus 0.1 L. Okay, so I hope the solution methodology is clear. Okay, so you may ask, like, why not choose control volume as like this that we initially chose, or why not choose something like the streamlined form? But we could have done that, but the thing is that this control volume is already given the question, so we need to approach the problem as given in the question. Okay, so that's why we need to choose the control volume that is given in the question, so that's why we have to deal with this kind of modifications. Okay, so I hope this is clear. Now let us look into the next question, and I will expect that you at least try the next question. I will not say it's quite difficult, but okay. Oh, I'm sorry for that. It seems I missed the question, but I'll just write it. I hope it's not that long. Just give me 1 second. Okay. So how I forgot the question, I don't understand. So it's question number 4, I guess. So it's a spherical balloon with the initial radius of r0. Okay, so it essentially means that r0 at R at t equal to 0 is equal to R naught. Okay, R naught through section 1 as shown as where area is A1. Okay, so area of this section is A1. Okay, and there is a uniform velocity V1 through this particular inlet and fluid density rho1. Okay, so all these terms are given here. And this is the initial density of course the air is being pumped with the initial density rho1. That will imply that rho of air or rho of air within the balloon at time t equal to 0 is rho1. Okay, so now it is given that the density of the air inside the balloon is a function of time, which is given by rho b t is equal to k times e to the power t by tau. Okay, where tau is a constant. Okay, where tau and k are constants. Okay, tau and k are constants. Okay, need to find the rate of change of radius of the balloon when the radius is same as r naught. Okay, so find the expression for the rate of change of radius of balloon when the radius is same as r naught. Okay, so you can give it a try. I am sorry that I forgot the question properly, so but I have written it here now. So you can give it a try. Let me give you 5 minutes. Just try it out again. Rate of change of radius will mean that rate of change of displacement is velocity, right? So you are dealing with again with the mass conservation. Okay, so start with the mass conservation equation. Try to substitute the values of say density, volume. In this case, volume of the sphere would be 4 by 3 pi r cube. But here also it will be a function of time. Why? Because the radius itself is a function of time, and density is also a function of time as shown here. So you need to take these into consideration. So start with the mass conservation. Try to solve as much as possible, and let's see whether your approach was correct or not. Okay, so I'm not expecting the answer by say 754, but at least try some things. Try to start with the mass conservation equation, substitute the values of as shown here, and then let's see when I show you the solution whether you are able to match with it or not. Okay, so I don't expect you to solve explicitly. Like, of course, if you solve, it's great, but even if you do not, I don't expect that you are starting it for the first time. But at least try it. Okay, try it out. Okay, so you can do that. I will give you say 4 more minutes, and then let's just try to see whether we can solve it or not. Okay. 2 more minutes. Okay then, so I think we can look into the solution. Okay, so okay, so so let's look into the solution. Okay, it's fine. So here, okay, fine. So this is the problem that we have in our hand, and it is given that density is a function of time given by this equation. Okay, rho b, this density of air inside the balloon, is a function of time given as ke to the power t by tau, where e is an exponential function. Okay, then from mass conservation we will get dou by dou t of cv rho dv plus surface integral of rho v r dot n cap dA is equal to 0. We cannot cancel it out because here both density and volume are a function of time. Okay, so we will take that into consideration. Or we have dou by dou t volume integral of rho dv plus 0 minus rho v r dot n cap. Why is 0? Because the outflux is 0 and mass is only coming inside the balloon, so there is only mass influx. Okay, and this one would be equal to rho a1 into v1, rho 1 into a1 into v1 as given here. I forgot to write it here. It would be rho 1 a1 and v1, or sorry, v1. Okay, then this would be equal to dou by dou t of rho bt times 4 by 3 pi r cube. Okay, because if say that if density has no spatial dependence, okay, density has no spatial dependence, then density can be taken out of this integral. I'm sorry, density can be taken out of this volume integral, and then volume integral of dv would be just the volume of the entire sphere, this 4 by 3 pi r cube. And again remember, r is a function of time. Okay, so I will just mention it so that there is no confusion. R would be a function of time. Okay, because volume is changing by what? It 4 by 3 and pi are constant, so it's only if volume is changing, it will mean that the radius is also changing. Okay, so we will have rho a1 v1 is a dou by dou t of rho bt times 4 by 3 pi r cube. Then you can take out 4 by 3 pi as it is a constant, numerical constant. Then dou by dou t of rho bt, dou by dou t of rho bt times r cube. Okay, we again use the chain rule of differentiation, right? So first take derivative of this, then leave it constant. So rho by dt rho bt times r cube. 4 by 3 pi is outside, so just r cube plus derivative of this 3r square plus dr by dt. Sorry, 3r square times dr by dt plus rho bt. Okay. Just applying simple chain rule of differentiation. Okay. Then rho 1 a1 v1 is equal to 4 by 3 pi. Then derivative of rho bt would be if rho bt is k exponential of t by tau, right? Then dou by dou t of this one would be k with constant, so k will come out. Now exponential will again be the derivative of the exponential will be again the same, so e t by tau times the derivative of t by tau would be 1 by tau, okay, times r cube, which is shown here, right, plus 3 rho bt r square dr by dt. Okay, now from the initial conditions that we have in our hand, we can apply that to, of course this gives us a nice relation. Of course, even if you leave it here, you will get some marks in the exams, of course, if it's a subjective type exam, but you need to find an expression for dr by dt. Okay, so for that you need to have you need to represent all dr by dt in terms of some given values, okay, some given constant values or known values. Okay, so you need to simplify it a bit further. But we know that for r equal to r naught, or at t equal to 0, r is equal to r naught, okay, and rho bt equal to 0 is rho 1, that is equal to k. How? You can see here. So rho b, let me write it here, rho b at t equal to 0 would be equal to k, e t would be equal to 0, so 0 times tau, so it is 0, e to the 0 is 1, so it will be equal to k, that is equal to rho 1, the initial air density. Okay, so this is equal to rho 1, then rho 1 a1 v1 is equal to 4 by 3 pi, k is constant, e to the power 0 by tau is again 0, right? Oh, sorry, e to the power 0 by tau is 1, with 1, then r is r naught, because at t equals 0 r is r naught, right? So r naught cube by tau plus 3k rho bt at t equals 0 is k, or rho 1, you can keep either of them, it's fine. I'm keeping k for right now, so it is 3k r naught square times dr by dt. Okay, now dr by dt would be, again, if we simplify this a bit further, just take this in the, multiply this here, so it will be 3 by 4 pi rho a1 v1 minus this term r naught cube k time by tau, and divide it by this one. Okay, it's very simple. I'm just writing it extensively. Then dr by dt would be equal to rho a1 v1 by 4 pi k r naught square minus r naught by 3 tau. We know that k is equal to rho 1, right? Then a1 v1 by 4 pi r naught square minus r naught by 3 tau, or dr by dt is equal to a1 v1 4 pi r naught square minus r naught by 3 tau. Okay, so this is your final answer. So if you look into the options, it will be this one, option number 8. Okay, so I think the time is up. I'm sorry, I started the session a bit late, again apologizing because of the fact that I had to attend an unavoidable meeting which came up all of a sudden. Okay, sorry for that. I will try to compensate it in the next week's session by taking some more examples regarding mass conservation, because primarily we will be dealing with momentum conservation in the next week, but still, okay, sorry for that. Then I hope you understood the problem, or should I repeat it just for the sake of today's session? Someone can say yes or no. Should I repeat it, or it's okay? Okay, thanks Saurabh. Then I think that's all for today from my end. Again, sorry for being late. Let's all meet next week. Okay, okay, then thank you.